Everyone. Good morning. I will be talking about threshold voltage loss variabilities in a 3D NAND flash memory array today. I'd like to thank IEEE and SRC first for this opportunity of presenting here today. I would like to extend my gratitude to all my co-authors and the funding agencies that made this work possible. So here's some outline of the things that I will be talking about here today. First, I'll talk a little bit about motivation and background, and then I'll go into the details of our experimental setup, and I'll discuss the results from our findings, and then finally I will conclude my presentation with a summary and some implications from our findings. NAND flash memories has been the primary choice for permanent storage of data for years, and it has been particularly successful, fueled by continuous technology scaling of 2D NAND flash memories. But it stopped at around 15 nanometer due to some unavoidable reliability issues. This is where 3D NAND flash memory comes in. Now, 3D NAND flash memory is a gate-all-around cylindrical transistor, and it can be grown vertically layer by layer. So there has been increasing number of layers over the years since 3D NAND flash memory came out. So right now there has been reports of 200s or 300s levels of layers in a 3D NAND flash memory chip. So in summary, 3D NAND flash memory revitalized the bit density growth per area, and there has been projections of 1000 layers by 2030, by the year 2030. And apart from this new degree of freedom in the Z direction, there has been logical scaling too. So right now, 3D NAND flash memory chips, a single cell can store even 4 bits of data. There has been reports of like even 5 bits per cell too. So right now, the 3D NAND flash memory has the lightest weight, smallest footprint, very fast read-write speed, highest bit density, and very low power operation. So practically, 3D NAND flash memories are the best candidates for space applications or extreme environment conditions. They have the most promise. Here on the left-hand side, I have shown a simplified diagram of a 2D NAND flash memory cell to just show what happens when a NAND flash memory cell is exposed to radiation. So electron-hole pairs are generated in the oxides, and some of them recombine quickly just after generation, and also electrons are more mobile compared to the holes. They're swept away. So the remaining holes, they either get trapped uh, or they annihilate the floating gate electrons. Now the number of holes that remains without recombination, they depend that number depend on the oxide electric field. On the right hand side, I have shown a graph from a published literature where the relationship between fraction of unrecombined holes and the oxide electric field is shown. If the oxide electric field is very high, there will be lots of remaining holes unrecombined, and if the oxide electric field is very low, most of the generated electron hole pairs will recombine. Now there's remaining holes, these trapped holes in the oxide, they reduce the total net negative charge in the gate stack. As a result, they reduce the threshold voltage of the NAND flash memory cells. In our experimental setup, we interface the flash chips with FTDI, and we control the FTDI with our computer, and the FTDI controls or sends commands to the NAND flash memory chips. To get the threshold voltages or the VT distributions, we use something called read reference method. The latest generation of chips support read reference method. In this process, we can sweep read reference voltage from its default level with an increment of 7.5 millivolt each time. And as the read reference voltage moves from left to right, we note down the bit flips from 0 to 1. That is the point we note down the threshold voltage, and we repeat the same for all the remaining threshold voltage levels. Now I'll discuss the results from our measurements, but first, not all cells lose similar amount of threshold voltage during irradiation. So here on the left hand side, I have shown the distribution for L7 state of a specific page from our chip, and it is very obvious from here that after 50 kilorad of radiation, the distribution has become wider, and also the mean of the distribution have shifted to lower values. So obviously the page has lost threshold voltage, and also the distribution has become wider. Now the reason behind this distribution becoming wider is we can explain it on the right hand side through this concept figure, where I'm showing three kinds of cells. One is blue in color, one is red, and one is green. So you see here that the blue color cells, they are not losing a lot of VT. They are shifting very little. The red colored cells, they are losing a lot of VT, and this green cell, they are in between. So because not all cells are losing threshold voltage equally, that is why the distribution is getting wider after radiation. Here we have sorted out three distinct groups. A group of cells that are losing a lot of VT, we call them TID prone cells. A group of cells who are not losing that much VT, who are barely losing VT, they are called TID tolerant cells. And of course, there are cells in between, which we call the median cells. On the right hand side, I have shown the trajectory of delta VT for each 10 kilorad radiation consecutively, and we can clearly show that the blue cells, the blue colored cells, they are barely losing VT over 50 kilorad. They are staying what they are, and the red colored cells, they are consistently losing VT. Now, what is the difference between these two kinds of cells, these blue colored cells and the red colored cells? What is the physical property that makes a cell TID tolerant or TID prone? So, what is the reason why some cells stay surprisingly resilient to radiation? So, let's look at some Venn diagrams. On the left-hand side, I have shown two Venn diagrams. The first one on the top left is a typical programmed cell which has electrons in its floating gate, and it has no defects in either of its oxide, blocking oxide or tunnel oxide. On the bottom left, I have shown a cell which have defects in the tunnel oxide polysilicon interface. So if we program one of these cells, the electrons will fill up these interface traps, and these electrons will create a very sharp band bending at the interface, which means the remaining oxide regions, in the remaining oxide regions, the field will become very weak. Now the threshold voltage loss or the positive charge yield depends on the oxide field. So because right now, because of this interface field electrons, interface trap field electrons have weakened the oxide fields, the net positive charge yield will go down, and the cell will not lose as much VT as a typical cell. Hence, we call this a TID tolerant cell. On the right hand side, we have shown a very rough estimate of if we reduce the blocking oxide electric field by 50%, what happens to the fraction of unrecombined holes? They also go down at around 50%, which is very low compared to the previous situation. We have three different evidence of our hypothesis behind the origin of these TID tolerant cells. The first one comes from the fabrication process of the 3D NAND flash cells. The 3D NAND flash chip is fabricated using alternating layers of metal and oxides. A hole is punched through this stack through reactive ion etching. Now this reactive ion etching is not a perfect process, so that is why the hole is tapered shaped, and the bottom region of this hole, or the bottom region of this stack, is very defect prone. The blocking oxide, the charge storage layer, the tunnel oxide, a thin polysilicon layer is deposited one after another, and then the central remaining hole is filled up with oxides. Now, because of this inefficient reactive ion etching process, the bottom layers of the stack is very defect prone, and as a result, the cells from the bottom layers of this stack will have very high number of interface defects in the tunnel polysilicon interface. Now, according to our hypothesis, if a cell have defects in the tunnel oxide and polysilicon interface, that cell will become a TID resilient or TID tolerant cell. So that is what we just see from our experiments. So here on the right hand side, I have shown measurements from two different chips that shows that the number of TID tolerant cells is high in the bottom layers of the stack and low in the top layers of the stack, which of course supports our theory that a TID tolerant cell will have defects in the tunnel oxide. For evidence 2, we did another experiment. We radiated the same chip twice. Now let's look at the band diagrams, what happens when a chip is radiated 2 times. So on the top left, I have shown a band diagram which shows a programmed cell, a typical programmed cell before the first irradiation. Now in this programmed cell, there are barely any defects. There are 1 or 2 defects in the tunnel oxide. The floating gate is storing electrons. This is before round 1 irradiation. Now this cell goes through irradiation round 1, then we get the chip out, and then we perform the measurements, we erase the blocks, and we reprogram the chip again. On the bottom left, the band diagram shows the cells that are reprogrammed after the first dose of irradiation. Now what happens during irradiation is electron hole pairs are generated, and because of this electron hole pair generation, there are new oxide defects also generated. And because the tunnel oxide electric field is very high, most of the defects will be generated in the tunnel oxide or tunnel oxide polysilicon interface. So on the bottom left figure, in the band diagram, we see that after first round of irradiation, this cell will now have some additional defects along the tunnel oxide polysilicon interface. And now if we reprogram these cells, these traps will be filled up by electrons and cause sharp band bending and weaken the electric fields in everywhere else. So it certainly looks like the TID tolerant cell we just described a moment ago. So when these cells are exposed to a new irradiation round 2, what will happen is we're expecting that these cells will behave as TID tolerant cells. So on the right side, here's the result from our 2 rounds of irradiation on the same chip, and we see that after irradiation round 2, the number of blue cells in the same chip have gone up, which means there are new blue cells being generated. And how? Because after the first irradiation, new interface defects are created, and a typical cell has become a TID tolerant cell right now. So these results clearly support our hypothesis. As the final support to our theory comes from a retention experiment, we left the radiated chips at room temperature, preserved the radiated chip at room temperature for almost 6 months. Then we again performed another set of measurements. So here on the plot, I'm showing the correlation between the VT loss during irradiation 6 months ago and VT loss during this 6-month room temperature annealing on the y-axis, and they have a good degree of correlation. And here's some interesting thing. The cells that lost a very small amount of VT, which means the TID tolerant cells, they are losing VT over these 6 months, which is natural. But the cells that went through heavy threshold voltage loss, let's say around 0.8 or 0.7 volt loss during irradiation, they haven't lost VT over the last 6 months. Actually, they have gained some VT. On the y-axis, the negative VT loss is actually VT gain. They have also gained some VT. So what is going on? So we can also explain that through band diagrams of our theories. So first, let's look at a TID tolerant cell. A TID tolerant cell will have electrons in the interface filled up. So these electrons will get detrapped quickly. And also the floating gate electrons, they can hop through tunnel oxide defects and through TAT, trap assisted tunneling mechanism, and get lost to the polysilicon and quickly lose some charge. So this is why the TID tolerant cells are losing some charge over the last 6 months, because they have lots of defects in the tunnel oxide. But a TID prone cell which loses a lot of VT during irradiation, what happens to them? They have barely any defects in the tunnel oxide, but but they have positive charge holes trapped in the oxides, tunnel oxide, and these holes are redistributing themselves toward the floating gate electrons over the last 6 months. And because these holes are moving toward the floating gate, they are actually increasing the VT of the threshold voltage. Now, what we can do to improve the radiation tolerance of a cell, we can thin down the oxide, uh, reduce the oxide volume so that a lot less number of electron hole pairs are generated, or we can incorporate defects in tunnel oxide intentionally. But it certainly has a trade-off, because doing either of these will reduce the data retention or charge retention capability of the cells. So we have to decide how much retention we want or how much radiation tolerance we want. In summary, we found that a certain fraction of memory cells are TID resilient, and these TID resilient cells are dominant in the bottom layers of the stack. They lose charge faster, and they can increase in number if we radiate the same chip again and again. So, and also we provided a physical explanation behind the TID tolerant cells based on pre-existing traps along the tunnel oxide interface. So thank you. Thank you for listening to me. I'll be open to questions after my presentation.